Okay. So like I said, this was yesterday's. Here's where the problem starts because it's not super clear. All that stuff, all this stuff in green is just like an intro to the unit. But here's the first example, right there. It's a multiple choice question, so see if you can get the answer yourself, and then we'll talk about it in. You can think for like a minute. In fact, I'll set a timer because I do not want to spend too long today. Here's 1 minute to think about what you think the answer is. Alright, don't get scared when this beeps. 2 seconds. Okay. I don't even know if that was like this. You may not have built up the ideas behind this to be able to answer this question yet, but the answer should have been C as in cat. Because watch this, you guys. Because watch this. If you look at this series, power series, then actually I just noticed that I think this is written wrong because I think it should be x plus 4 to the n. But hopefully that didn't throw you off. Because this is the important part that you look at. This x plus 4 to the n tells you where the center of the series is. Like this series is centered where? You tell me. Yeah, -4. This x plus 4 tells you the center of the interval of convergence is -4. And then the fact that it tells you that the series conditionally converges at x equals 1 basically tells you that that's the endpoint of the interval of convergence. Because if it wasn't an endpoint, if it was within the interval of convergence, then it would converge absolutely. That's what the ratio test said. Ratio test says if the limit had been less than 1, then it would converge absolutely. This is me very quickly summarizing it. But if the limit had been less than 1, then the series would converge absolutely. If it's greater than 1, then it diverges. So the only chance it has of converging conditionally is on the endpoints, like when the limit is exactly equal to 1, which is what the endpoints are. If you can look back through your thing. So you know that this x equals 1 has to be an endpoint, like the end of the interval of convergence. And so now you know that your radius of convergence is 5, right? From here to here is a distance of 5. Cool. So that means you could go 5 this way as well. And get to -9, which is why there's all these options about -9. But the thing is, you knowing what this endpoint does, like whether it converges or diverges, doesn't tell you anything about what that red endpoint does. So you don't know if the series will converge at 9 or diverge at -9. There's no way to know, just off the information given. But what you do know is anything within this interval should converge absolutely. So that's why I'm saying -2. Oh, shoot. -2 right here for sure converges because that's within the interval. There you go. So kind of a hard problem, but I thought it was a good one. It makes you think a little bit. If you don't believe me and you need convincing, here's the work we did yesterday. And you can see that one endpoint converged, but the other endpoint did not converge. So the fact that this 7 converged doesn't mean anything about the 3. The 3 could have converged and it could have diverged. You don't know. Cool. All right. Now 7-7 is done, and 10-7 is done, and we can start the last section of the whole curriculum, which is 10-8. And 10-8, it talks about representing functions as power series, which is exactly what we were doing 2 sections ago. So, but the only I guess there's a couple differences. One difference between 10-8 and 10-6 is that in 10-6, when we were doing the power series, like approximating e to the f with a polynomial, that was always like, based on those problems, they were always finite, like approximated up to 6 terms or whatever. Now you're going to talk about infinite polynomials, but it's not any different. It's like the same exact process. And then the other difference between 10-8 and 10-6 is that this one focuses on the 4 most important, like most applicable, most special power series that you have to know. One of them being, I don't think I want to read you all this because this is easier to explain once we're in a problem. But one of the most important ones is this one with geometric series. This was like maybe on the very first page of this whole packet, was that we said that if you have a geometric series, then we know for sure that if it converges to this, where A is the first term. And then R is the ratio. I guess I didn't need to draw an arrow to that R. Okay. So if you can use that, to your advantage to say, well, if that's true, then I could represent this function 1 over 1 minus x as 1 times x to the n. In other words, make A be 1 and make R be x, and then you get this function. Cool. The only thing is that, watch this. Here's me going to Desmos real quick. 1 over 1 minus x. If I'm trying to represent that function, we just agreed, I can just make this a geometric series. So sum from 0 to, Desmos can't do infinity, but if you just do enough terms, like 30, then it gets pretty, like, it's basically the same thing. And we said this would be 1 times x to the n. And you can see this does a perfect job of approximating that red function up to a point, though. What the hey? Then it goes really bad job. And it's not the fact that I only went 30 terms. If I go 31 terms or 32 or 33 or 34, you can see it doesn't get much better. If I go 50 terms, it doesn't get any better. 100 terms doesn't get any better. So do you guys know, without me saying, how come it does such a great job? Boom, boom, perfect. Oh shoot, not even close. Can you think of why this series isn't exactly that function? Maybe it's like, it's kind of a hard question. But the thing is that this series is only equal to that function if the if like the series converges. You know what I mean? So for a geometric series to converge, you need the R value to be less than 1. So in other words, you needed this x to be the absolute value to be less than 1. Outside of that interval of convergence, that doesn't, like, this series does not represent that function at all. Which is why if we go boop, 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 you can see where it starts trailing off is right there at 0.999. Like right at 1, it stops being a good approximation. Cool. So this has to do with the interval of convergence, which will be relevant in a second when we start doing problems. But as long as x is small, then this can sometimes be a helpful thing to approximate this function with that series. All right. Then, that's exactly what I said. And now here's example 1 that says, based on what you know about the fact that this series equals this this series equals that function, can you find a series that represents this function without having to do like f of 0, f prime of 0, f double prime of 0, etc. Can you think of a way to edit this series to get to this series? If you can see it right away, great. If not, I don't want to spend forever on any one problem because I want to get through the curriculum. You see it right away? Anybody? Do you see it? Yeah, exactly. Look, if this was just 1 minus negative x, then we get 1 plus x. So in other words, what I'm saying is f of x is 1 minus negative x down there. And so basically, if I just flip the sign of this x, which would represent that x, then I'd get this function. So watch this. This series. Oh shoot. This series should equal that. Which kind of feels like cheating, but this is the trick for a lot of these questions, is that if you can edit one of the series that you know really well, like one of these 4 special ones, the 4, I guess I'll spoil some stuff. The 4 special ones are going to be this geometric one, e to the x, sine of x, and cosine of x. Those are 4 that you have to know, or it would be good to know off the top of your head. And if you can edit one of those to get this new function, then you're kind of allowed to do whatever you need to do to edit those. One more thing before that question is that if you wanted to make it look more like the other series that you've seen, you could take this -1 times x to the n and make it -1 to the n times x to the n. And that might be even what's on that poster. Yeah, look at it. That second one on that poster is exactly this function. Question.
Why do you want to change it to a power series?
Sometimes, just in general math, I'm trying to think. When I was doing my master's project, I remember this specifically came up, and I was like, oh, this is why these are helpful. But I don't remember exactly the context. Rats. But there are times where, like, maybe you want to approximate a value of this function, or maybe this function does a good job of bounding some, I think that's what it was in my master's program. I'd have to look back into it. But I have a really good answer, not necessarily for this one, but for like e to the x sine of x and cosine of x. Like when you're calculating that in a calculator, the calculator, like let's talk about e to the x. When you take e to the 7th power, for example, the calculator itself isn't doing 2.718 or whatever to the 7th power. It's doing the polynomial version of e to the x and plugging in a 7. So your computers and your calculators way prefer doing the polynomials, like the power series, over the actual value of the transcendental series or transcendental function. So what I'm saying is your calculator does this over this. Like it does the power series over the sine. So there's one application. Cool. Other question? Okay. Well, that's the trick for most of these. So see if you can watch this. Watch this. This next one, you're trying to see, can I edit this function somehow plug in the right numbers for x and whatever, so that I can get that function right there. Here's like 30 seconds for you to mess with that and see if you can get from this function to that function. And you guys don't know what rules apply or whatever, but basically, let me these 4 things on this. So you can do anything you want. Like basically, if you want to multiply a series by x, you're allowed to. If you want to replace the x with a 3 minus x, you're allowed to. That's what these 4 things tell you. You could either take the derivatives, integrals, anything you got to do, you're basically allowed to do. It's not cheating. All right, 30 seconds, see if you can get that series right there. Okay, was that 30 seconds? Did you get an answer, anybody?
What do you say, guys? You just add 1 to the end, right?
Add 1 to the end. Because why?
Well, the highlighter of the x, modifies the x, so 1 times modifies the other one. Yes. You can add 1 outside of it.
Wait, I don't see it the way you're seeing it.
Where else would you add do it to modify like the?
Like what I saw is, okay, if I don't want a 1 up there, but I want an x up there, then I change this 1 to an x.
Oh, this is x on top.
That's why I thought you were saying add 1 to the power. But yeah, I mean, I thought you were getting there because then you would get x times x to the n, which is x to the n plus 1. That's what I thought you were saying. But even then, you're still missing a small thing. What are you about to say?
Is it 1/2 x is it?
That was sweet. Okay, that was sweet. So for this one, you kind of have 2 options. If you saw it like me, then maybe you said, I want to change this x, or sorry, I want to change this yellow 1 to this x. So let me change that yellow 1 to an x. X times, and then I don't have 1 minus x. I have 2 minus x. So I got to change this blue x to. Let me write it like this. If I write it like that, then you can see 1 minus -1 will be the 2, and minus the x will be the minus x. So if you saw it like me, you might have written this like, now it's 1 minus something, so this something could take the place of that. And this should match that function. From 0 to infinity, that should be equal to g of x. Or you could have seen it. How did you see it?
I just thought if you put 1/2 on it, it would like make it a denominator. So
That's the thing, is that I saw this like, oh, this is almost it. It's just 1 away. Like instead of it being 1 minus something, it's 2 minus something. So let me just subtract 1 from it, basically. But Bryce is seeing it like, here's one good answer. Bryce is seeing it like, if I just divide this by 2, then it'll be 1 minus something, and then I can treat this more like the function that I'm pointing at right now. So the other option, which is actually the better way to write it, is to treat this like g of x equals x over 2 minus x. If I just basically factor out 2 down here, then that's the same thing as x over 2 times 1 minus x over 2. And now you could even go like this. Now you could even go like this. Watch this. If I take out an x over 2, then this is really helpful because this part right here looks exactly like this part right here. Except for instead of it being 1 minus x, it's 1 minus x squared. But you can just change in your power series. Let's say green answer is good or this answer is good. Where I do 1 minus 1 over 1 over 1 minus x over 2 would be that series. I hope you agree. 1 over 1 minus x, this series. So if I just change the x for an x over 2, that would be this function. But I have this extra x over 2 in the front, so I can just multiply by an extra x over 2 on the front. And then you're smiling, then you've matched the thing. And if you're like, I don't believe you, then watch this. Let me show you on Desmond. Also keep in mind that I said this purple answer is a little bit better because watch this. There are my two answers. Okay. I wanted to match this function. Some of us saw it like the sum from 0 to infinity. Again, I can't do infinity, but let me do 50. Some of us saw it like, let me subtract 1 from this 2, and then I have 1 minus something like I like. So we got this green answer. X times.
Should we get an x on the top for the top function?
Oh, good job. Okay, there you go. Now you can see our green answer matches this function very, very well, and that's how we know we did it right. But our purple one, watch this, sum from 0 to 50 of x over 2. I know you can simplify this a little bit, but let me not. Let me write it exactly like we did over here in purple. X over 2 over, or times x over 2 to the n. Look how the purple one matches it a lot longer. So that's why I'm saying the purple answer is a little bit better. And that has to do with something that I forgot to talk about in the last example, even though it says it, is that this interval of, you can plug more numbers into the purple one and still have it converge. It's interval than the green one. But both of these are correct. It's just you can write these in different ways a lot of the time. Cool. Okay, so now you're like, I've been talking about this problem for 45 minutes, so we must be done, right? Wrong, because look at, if you read this problem, it said determine its interval of convergence. So I got to teach you how to do that real quick. But let me make some more room for myself. It also said it for the last one, but I don't want to go back because we'll spend forever on this problem. Okay, so interval of convergence for these, I'll just do it for one, like the green one that we started with, and then I'll tell you how this one is the same thing. But the interval of convergence for any geometric series, remember, this will converge as long as x is less than 1, or really the absolute value of x is less than 1. That's just always true for geometric series. So since I wrote a geometric series here with the ratio being what I'm underlining in green, I just need that underlying thing to be less than 1. So basically, I'm just solving this equation, and that'll be my interval of convergence. Okay. Well, I should say, if you wanted to and you always wanted to do the same thing every time you're asked for interval of convergence, you could always do the ratio test on this, like we were doing yesterday in 10.7. But in this case, you can take some shortcuts because this is geometric and you know that this is the interval. But anyway, here's me solving this. Remember, absolute value less than 1 means that that thing has to be between 1 and -1. And now if I just add 1 to both sides, I get 0 less than x less than 1. There's my interval of convergence for the green one. And if you do the same thing for this purple one, then you see why the purple one has a bigger radius of convergence. Because for this one, you need the ratio, which is x over 2, to be less than 1. And if you solve this one, you get that this should match from -2 to 2. That's the interval convergence. Question.
So when you add the -1 from the green interval of convergence, you only add it to one side?
Oh no, I'm stupid. Good job. Great catch. Yeah, you should add this to both sides. Good catch if you didn't see what he was saying. That should be 0 to 2. Sorry, good job. Okay, and then one more thing just to like really solidify. That's why this purple one is matching so well up to -1.9. Again, that's only because I want 50 terms. If I want more, it would match all the way to -1.9999999. That's why I matched -1.9 to all the way up to 2. You can see 1.8. And then the green one matches so well up to 2, but stops at 0, just like we said. Oh, okay, I see. It's all starting to connect. Okay. Let's go fast because I wanted to get through at least one of these. Example 4. All right, find the power series for that function and determine its interval of convergence. Okay. So I think it's worthwhile. You guys take 30 seconds to think about how you could match this from your baseline of that. And again, there's going to be many ways to do it. One will be objectively better because of the interval of convergence, but either one is good. Oh, this died probably. Is that right? Alright, keep thinking, don't look at the board if you don't want hints. But I'll show you my 2 ways of seeing this.
Whenever you're doing the radius of convergence, do you want to do that for the
Yeah.
do like the next one?
Yeah. Nice. Okay. See if yours matched mine if you're not still working. You could have seen it this red way or you could have seen it this green way. The red way would be to say, oh, the 1 minus is missing, so it must have been 1 minus 1 to cancel those, and I just got left with the 3x. In which case you would have gotten this red series. Or you may have seen this like, oh, the x in this purple function was multiplied by 3, so let me factor out that 3 and mess with it that way. That would be this green way, and you would get this green result. But both of those are good. The green one is slightly better because it has a better radius or like interval of convergence. But either one of those is good. Did somebody see a different one? Yeah.
Is the interval convergence like a lot of times better when there's a fraction?
Yeah, because like this 3x, well, it'll be easier if we just find it. So like, it tells us to find the interval of convergence, so let's do it. But I'm gonna go fast. We know we need the ratio to be less than 1. So this needs to be less than 1, meaning that 1 minus 3x needs to be between 1 and -1. And if you solve this equation like you did in algebra 1, subtract 1 from both sides, you get -2 less than -3x less than 0. And then divide by -3, and you may not remember that when you divide by a negative, the signs of the little alligators flip. So I'll let you worry about this on your own, but you will get 0 less than x less than 2/3. There's the interval convergence for the red one. And so what I'm saying is this factor in front is, like, when you divide by it makes your interval smaller, whereas having it a fraction made the interval bigger, like when we multiply by it. And that's why this red one is worse than this one, because this one doesn't have a factor of 3 in front, so it's not going to shrink the interval of convergence when you solve it. This one will just be 1 minus x less than 1, which means 1 minus x is less than 1 and greater than -1. Subtract 1 from both, and you get -2 less than x less than 0. And then take away the negative, and you get 0 less than x less than 2. That's the interval for the green one. Cool, so the green one would be a little bit better. And then, like I said, if you're confused or you're not convinced, I gotta move fast because I don't want to keep learning into Tuesday. I want to finish this on Monday. So, last thing I wanted to do is that sometimes you can't match this purple function exactly just by messing with the x or subtracting or dividing or whatever. But a cool thing you could do is take derivative of the purple or an integral of the purple and get its power series that way, that's when it starts getting pretty crazy if it wasn't crazy already. But look, let me get this all on one page so it looks nice. That theorem right there at the bottom of your page basically says that if you have a power series that you know for a function and it has radius of convergence greater than 0, then the derivative of that will match the derivative of your function, and its radius of convergence will also be the same. Although the behavior at the endpoints may differ, but you can worry about that later. So basically what I'm saying is I don't know a power series for that dude, but I do know the power series for its antiderivative. These always make me think super hard, but watch this. What I'm saying is this a little bit, once you see the trick, you'll be able to like figure this out on your own. But this function right here reminds me of the derivative of this function right here. Let me call this g of x. Just so you know, it's a separate thing that I'm doing off to the side. But g of x is equal to that. And if I took the derivative of this, I think I get exactly f of x or negative f of x or something like that. I think it's exactly f of x. But watch this. Let me convince you. First, to take the derivative of this, if you want to do the quotient rule, go ahead. But let me treat this like a chain rule. So there's g of x exactly, not the derivative yet. That means that g prime would be equal to -1 times 1 minus x to the -2 times the derivative of the inside, so times the -1 in here. Oh, and if you simplify this, you get -1 times -1 is 1, and then 1 minus x to the -2 is exactly this. Convinced? You good with me doing that? Okay, and then why is this helpful? Well, it tells me that g prime of x is exactly equal to f of x. Yes? Okay, all right. Well, that's good news because g of x, I know the exact series representation of g of x. You know what I'm saying? It's like the one we've been using. It's the geometric one. So g of x now off to this side, and then we'll be done. G of x is exactly equal to from 0 to infinity of x to the n. And then now here's my final point. We just agreed that if I took the derivative of g, I'd get f. Well, then let me take the derivative of this purple series, and then I'd get f. And I think the first time you do this, it feels like cheating, but if you just think about the series written out, like 1 plus x squared plus x cubed plus x to the 4th, etc., then you can see why this is okay to do. But yeah, just take the derivative of this. You would get, bring the power down and subtract 1 from it. You would get n times x to the n minus 1. And there you go. There's the power series representation for that one. Do we have time? Yeah, look, let me convince you. One over 1 minus x squared, we said should be the sum from 0 to 50 of n x to the n minus 1. Nope. Okay, you can see it does indeed match it as long as the x is less than 1. Or like between negative 1. Okay, so final step of this red problem, it says get this red series and determine its radius of convergence. Okay, last thing I'll say, and then you can go home and think about all this. I know I went through it fast, I'm sorry. Is that since the purple radius of convergence was 1, in other words, this had to converge. This had to converge only when x is less than 1, meaning its radius is 1 right here. Then its derivative also has a radius of 1. That's what this theorem says. The radius of convergence is 1. Luckily, they didn't ask us for the interval of convergence because it could be that the endpoints may converge on the original but not converge on the derivative or vice versa or whatever, but they didn't ask us that. Cool. Okay. Question, Dean, or no? Okay, question.
You use this like method on any like
Yes. I mean, it has to be pretty specific because we only have 4 series that we could really mess with. It's the 1 over 1 minus x, the e to the x, the sine of x, and the cosine of x are the ones that you'll see. So it's pretty limited to the derivatives and integrals of that, but yes, you could. The most useful one we'll do on Monday, the natural log. Didn't I see another hand though? Oh, okay. Well, good job. This was super, super heavy. If you leave and you say, what the heck just happened in this class, I would totally understand that. But at least you have the video to, like, go rewatch at 2 times speed, and then you'll be like, oh, okay, I understand. And on Monday, we'll, like, go back over the same exact stuff, and hopefully you feel better about it. All right, that is all from me. Good job. See you guys later.